Let's look at the function y equals x minus 3 times x plus 5 times x minus 7. This function is a product of three linear factors. Each of these things in parentheses is itself a linear function of y, in other words. If we were to multiply these out, it's fairly obvious, we use the distributive law and so forth, that the form of what we get would be ax cubed plus bx squared plus cx plus d. Now, this is a standard form of a polynomial. Okay, anything of this form is a polynomial. The polynomial, we say, has degree 3. That's the power of the highest term. These terms should be familiar with you, but if they aren't, jot them down, but at least make sure you understand them. Okay? This would be the factored form of the polynomial. Now, we're really interested in the factored form. We're not usually interested in this form because it doesn't tell us that much. If we can get the polynomial into its factored form, then we're in good shape. Now, we can't always factor a polynomial into linear factors like we have here. Sometimes we can always factor it into linear and quadratic factors. And the quadratic factors don't always then have zeros, so they don't always reduce to linear factors, as we're going to see. But in any case, if we have one that is a product of three linear factors, if we can find those factors, we can easily tell a lot about the graph of the function. For example, one of the first things we look at when we graph a function is where is it zero? What are the zeros of this function? Well, in order to make this function zero, all we've got to do is let x equal 3 or negative 5 or 7, because if x equals 3, for example, then x minus 3 is 0, and since that's multiplied by the other factors, the whole thing will be 0. Similarly, if x is negative 5 or 7. So we can begin sketching our graph by putting the zeros down, negative 5, 3, and 7. Not only are those zeros of the function, they are the only possible zeros of the function, because there's nothing else that you can put in that will make this product 0. Anything else that you put in isn't going to make any of these things 0, and you don't multiply three non-zero numbers and end up with 0. So these are the only possible zeros of the function. Another point that we always try to find on a graph, or almost always, is the y-intercept. That's usually very easy if there is a y-intercept. And the y-intercept, of course, occurs when x equals 0. We're at the 0 point of the x-axis when we're on the y-axis. And we plug in 0 here, and we're going to end up with negative 3 times 5 times negative 7, which is 105. Another thing that we want to look at is what happens when x is a large negative number. What happens when we get out beyond negative 5? Well, if we're out on the other side of negative 5, anywhere on the other side of negative 5, it turns out, all three of these factors will be negative. Okay? Everything's negative. If x is a very large negative number, of course, all these are going to have to be negative. If x is negative 1,000,000, then these are all practically just negative 1,000,000. If we multiply three negative factors together, large negative factors, we get a humongous negative result, which means that this graph, as we cross negative 5, is going to have to take off down here faster and faster. It's got to reach humongous fairly quickly. Humongous in that direction. On the other hand, if x is a large positive number, actually any number greater than 7 will give us three positive factors, and a large positive number is going to give us three really large positive factors, which means we got an extremely large positive, so the function has to go up this way here. And once we know that, once we have all these arrows drawn to see what happens at large positive and negative, and we have our graph points drawn, the graph points that we can easily find, it's pretty easy to go ahead and fit a curve that satisfies those conditions. Just remember that this curve can only go through the x-axis, only touch the x-axis at zeros.